Welcome back, everyone. This time around, I wanted to take some time to talk about the ways that I think about coordinate systems in terms of really just their shape, the kind of shapes that lend themselves really well to working with each of these individual systems, and kind of explain to you how I use that to identify what types of regions are best represented with different types of coordinate systems. So in this video, I'm going to talk a little bit about how points get plotted in the Cartesian, cylindrical, and spherical coordinate systems, and use that to identify what types of surfaces and regions you really want to try to use each one of these for. So let's go ahead and get started with the Cartesian coordinate system for this. So when I talk about the shapes of the coordinate systems, what I mean for this is that each one of these coordinate systems has kind of a basic shape that is related to that particular coordinate system. And the Cartesian coordinate system is no exception from this. I mean, you look at cylindrical and spherical and you're like, okay, well, we have cylinders and spheres. Well, Cartesian coordinate system is also known as the rectangular coordinate system. And let's take a look at this and see why. So if we take our X, Y, and Z axes, like so. So X, Y, Z, and suppose that I want to plot a point. X, Y, Z. Well, in order to get to that point, I had to have, say counted out a certain number of X components, and then a certain number of Y components, and then a certain number of Z components, like so. And one way, I mean, this really kind of winds up filling out a rectangle in this sense, because, I mean, these are just sides of a rectangle. We've got a bunch of 90-degree angles here, and we can kind of think about this, okay, well, we had to go that many components up, and this many components over, and then same idea again here, back in the Y direction, and then we can also approach it from this way, Y direction first, like so. And what you wind up filling in here with each of these different directions is, well, a rectangle. Okay, so we can think about using the Cartesian coordinate system as this point exists on the far back corner of a rectangle that has sides X, Y, and Z. And so this creates the shape of a rectangle, which has all these really nice corners in it, really nice flat faces on it. And so because of that, because, these points identify well with flat surfaces and nice corners, a lot of times you're going to want to use Cartesian coordinates when you're talking about shapes that have really flat faces and lots of corners. So lots of corners and nice flat faces, all flat faces, okay? I mean, there's no curvature here. Everything's nice and flat, okay? So things that you're working with, like a plane or a line or like a tetrahedron or something like that, any of those kinds of nice angular shapes, you're going to want to start working with the Cartesian coordinates. I mean, even when you're integrating and trying to set up that type of domain, this is what you're going to want to stick with, the X, Y, and Z coordinate system. All right, let's look at cylindrical coordinates. We can kind of apply the same idea here. I'm going to plot another point. So if these are axes like so, and suppose that I want to put a point right, I don't know, we can put it here, for example, okay? Now, when we're trying to identify this point using cylindrical coordinates, well, we kind of drop this down here and say, okay, and actually I'm going to use a different color instead of black. Let's use this green here. Okay. So we're going to drop the point down to the XY plane, and then we have this little radius that comes out from the origin like so. We call that R, and that tells us how far away from the origin we were here. And then we have this nice little angle from the x-axis that we call theta, that tells us how far in the left and right direction that we would have gone there. Well, as the name might suggest, this point and this way of talking about different points in the system actually just has to do with, where would it be located on a cylinder and what size and shape is that cylinder? Well, in this particular instance, we're talking about a cylinder that has radius r and height z. So we can kind of fill this out with a cylinder. If I can draw it successfully, it'll look something kind of like this. The back part of the cylinder, that where the cylinder is centered at the origin, has height z, radius r, and then theta really just kind of tells us, maybe if I get kind of a darker green for theta here. Theta really just kind of tells us where on our cylinder we're actually located. So again, the information that we get from this is a cylinder. It's located somewhere on a cylinder with radius r and height z. And the location on the cylinder, or maybe I should say location going around the cylinder, because it's really just kind of like, okay, it went out this way, and it went up this way, and then it can be anywhere around here along the top edge of the cylinder, and that anywhere around there is just specified by how far theta got to go around the circle. So our location around our cylinder, or around top edge of cylinder, is specified by theta. But anyway, all of this is to say that when we're working with cylindrical coordinates, we're thinking about all our shapes in terms of some form of a cylinder. Either it's some combination of cylinders or some particular location on a cylinder or something like that. And so when we're thinking, okay, in terms of cylinders, we want to start working with surfaces that are, well, cylindrical, right? They have nice flat tops and then they're kind of round around the edges. So they're ideal for surfaces. Let me go back to the black one now. So ideal for surfaces that have round sides and that have a flat top or a flat base. So, I mean, like in some way or another, it looks like a cylinder, okay? Now, I mean, like it may not be exactly like a cylinder, but if you can kind of think, okay, it's some modified form of a cylinder, then cylindrical coordinates are probably going to be your best bets. Finally, we're going to look at spherical coordinates. And when we're working with spherical coordinates, let's go ahead and plot a point here. Let's see what this looks like. Okay, so there's X, Y, Z axes, and we can put our point, I guess, again, out here. Now, in this particular instance, when we're working with spherical coordinates, everything's in terms of like a row and then two other angles and stuff like that, where rho is the length of the distance between the point and the origin, like so. And then we say, okay, well, how far along, like where is it located on the relative to the X and Y plane? By saying, let's project it down to the XY plane, and then kind of look at a similar angle here, theta, just like what we did with the cylindrical coordinates. This is a theta. It doesn't really look like one though. Makes it clearer. So that's our theta. And then the other piece of information we have is, okay, how far up and down did we go? That's phi, right? And this can be thought of as being located somewhere on a sphere. Okay, so this is somehow connected to some big sphere that has radius equal to rho. So we can kind of fill this out like so. And this is somewhat depending on my artistic ability. Okay, there we go. Okay, so here's our sphere. Apologies for the lopsidedness of it. But this is a sphere here that contains our point that we were looking at here. And this particular sphere has, well, its radius. We can kind of think about this as having a radius rho. So the distance all the way around the sphere is still rho. But then we use our information about phi and theta to recognize, okay, where on this sphere did it go? So this is a sphere with radius rho. Location on the sphere is specified with the direction that the, I think about this as kind of being like a little arm that gets to swing around this whole space. So it's the direction of the arm that has length rho, and that direction is given by the combination of phi and theta. Oops, theta. Okay. So since everything here is in terms of spheres, like we're talking about, okay, again, combinations of spheres, where are things located on spheres and stuff like that, this works really well with surfaces that are really just round everywhere, okay? And so you're going to be looking for things that have round sides and have a round top and or bottom. Or face, okay? So like if you want to compare and contrast a little bit, you can think about, okay, the typical ice cream cone shape that we'll see in a lot of things, that's really great for spherical coordinates because it doesn't have a flat top to it, whereas just the plain old cone is great for cylindrical coordinates because it does have that flat top to it. And yeah, so again, it's just the idea that, okay, you might occasionally see that there are some kind of straight edges in spherical coordinates, but the big thing here that you're going to look for is that the overall overarching shape is that it would fit really well into a sphere. If it looks like something that would fit really well into a sphere and does not have both a flat top and a flat base, then that's a really solid choice for spherical coordinates. So yeah, this is just kind of like the main idea behind what these types of things look like. Again, we're just figuring out better ways to express different types of shapes and regions and points, depending on, you know, if it's kind of shaped like a circle, why not use it in a way that it naturally describes circles? Well, that would be like spherical coordinates or cylindrical coordinates or something like that. So in my next video, I'm going to go into a little bit more depth working with certain examples on how to set up like integrals based off of what the shape of the domain looks like. So stay tuned for that, but hopefully this kind of gives you an overarching idea of when to use each of these types of coordinate systems. So I'll see you guys next time.